Okay, so here's the second half of the capacitor video. Okay, in the previous video, we really just defined what capacitance was, what a capacitor is, how do we do some calculations with capacitor, and capacitance. Okay, now what we're going to do is look at how do we find the E field, right? The electric field in a capacitor, as well as the potential difference between the plates, right? If we're not given that information. Okay. So really what we're going to do is we're going to revisit some of the stuff from last unit. Okay. So to determine the electric field of a capacitor, we are going to use our good old friend Gauss's law. Now, I'm going to write Gauss's law just a little bit different, okay? Because a lot of times we're going to look for Q, okay? And so I'm going to write it, solve for Q. So I'm going to say Q equals epsilon naught. So if you remember Gauss's law, as we talked about before, was the surface integral of E dot dA is equal to Q over epsilon naught. So all I'm really going to do is I'm going to take this epsilon naught and multiply it to both sides. And that's how I'm going to write this, rewrite Gauss's law. Okay, so it's going to be Q equals epsilon naught, the surface integral of E dot dA, right? Now, again, you don't have to like go, oh no, there's a surface integral. Remember, a lot of times the answer to this surface integral is just going to be E times A. Okay. And so that's all you have to worry about. So what happens is this law will now allow you to find the electric field around a capacitor of any geometrical shape. Okay. Now, to find the potential difference, we're going to do our equation from before. We're going to do negative the integral of E dot dr. Okay, now our limits of integration are going to be from the negative plate to the positive plate. Okay, and so and really it's just going to be separated by a distance d. So sometimes that r can be replaced with d. Sometimes you can leave it as r and just replace whatever you want into d. Okay, but again, and you can see it in this diagram to the right here, the path of integration is going to be from negative to positive. Okay, so let's look at an example, right? So derive an expression for the electric field and potential difference between a parallel plate capacitor. The plates have an area of A and are separated by a distance of D. All right. And so you have to remember, we've done this before. We did this way back when we talked about E fields. Um, but what we did was we used, you know, we used Gauss's law, but we really did incorporate it into the capacitor piece, right? And so and so here's just another way on deriving that expression. Okay, so first let's find the E field, right? And so epsilon naught, the surface integral, right, of E dot dA is equal to Q enclosed. Okay, and so what we're going to do is, again, don't be afraid of the integral because it's just going to break down to be E times A, right? And that's going to be equal to Q. Now, if we have rectangular parallel plates, if we have circular parallel plates, we can figure out that by just plugging in that A, okay? And so I just now solve this for the E field, and I'm going to get Q over epsilon naught times area. But one thing to remember, Q over A is sigma, right? That's surface charge density, right? And so Q over A is sigma, so that's just going to be sigma over epsilon naught. And if you remember when we did this way back with E fields, that's what we ended up with, was sigma over epsilon naught. Okay. And now let's find the potential difference. So delta V equals negative from negative to positive of E dot dA or dr. Now my R is going to be D, right? But I'm not going to put dd. I'm going to just leave it as dr. So I'm going to say delta V equals negative from 0 to D, right? Because this is 0, this is D, right? That's the distance between them, right? Of E dot dr. Well, E dot dr is simple. It's just going to be, think about the E field as constant, right? And so we're going to do from D, right, from 0 to D. And so what happens really is this negative sign flips everything, right? And so it just becomes E times D, but I know E is sigma over epsilon naught. So there is my potential difference, right, between my parallel plates. And so if I do that, it's going to be QD over epsilon naught A, right? That'll be my potential difference if you're looking for it in other terms. So so really the difference between the E field is a lot simple, right? Because sorry, this problem is a little bit easier because of this nice geometrical shape. Let's see what happens when we do it if it was a cylinder, right? So if we had a cylindrical capacitor, okay? And so here we go. Using Gauss's law, derive an expression for the electric field between two cylinders, and then derive an expression for the potential difference between the two cylinders. Okay, so the first part, E field, right? So epsilon naught equals the surface integral of E dot dA equals Q, right? Okay, and so again, this is going to be epsilon naught equals or times EA equals Q. All right, now, so we're going to say epsilon naught equals E. Now, what is the surface area of a cylinder? Well, it's just going to be, in this case, it'll be the right the area of the rectangle if I cut it open and lay it flat. So one side will be 2 pi r, the other will be L. Okay, and so my surface area will be 2 pi r L equals Q, and I just saw this for E. So E equals Q over epsilon naught 2 pi r L. I apologize for my pen. I don't know what's going on. I may have to clean the iPad here shortly. Okay, now let's find the potential difference between them. And so again, it's going to be negative E, right, from negative positive E dot dr. And so delta V is going to be equal to um, negative from our negative plate is our outside, so it's going to be B to A. Okay. Again, we're going from the negative plate to the positive plate of E, which is what we found for the first part of this question. So Q over epsilon naught 2 pi r L, right, dr. Well, the good thing is pretty much all of this except for the r is constant. So it's going to be Q, right? I'm going to leave the negative sign over there, right? And so negative, right? So it's going to be Q of epsilon naught 2 pi L, right? The integral of 1 over r dr. Okay, and we're going to go from B to A, right? Our negative plate to our positive plate. Okay, and so now the integral of 1 over anything is going to be the natural log of that thing, right? And so I'm going to have Q over epsilon naught 2 pi r L, or 2 pi L, natural log of r evaluated, and it's going to be negative, right, from B to A. And so when I plug that in, I get delta V equals Q over 2 pi epsilon naught L. I know I rewrote everything now all of a sudden. I got negative natural log of B minus natural log of A. Sorry, I in one step have incorporated the negative sign. Okay, but if you remember your natural log rules or your log rules, anytime you subtract logs, it becomes division. So your potential difference between in a cylindrical um, in a cylindrical capacitor will be Q over 2 pi epsilon naught L natural log of B over A, right? I know it looks like a 2, I apologize, but there's our potential difference, okay, for a cylindrical capacitor, okay? Now, let's talk about, again, we talk about how capacitors store energy, right? And so because there's a storing of energy, there is a potential energy, right? And we call it the electric potential energy. And so you can find the electric potential energy two ways. You can use the equation 1 half Q delta V, or if you want to bring in the capacitance, you could say it's 1 half C delta V squared. Okay. And a lot of times you can drop the delta, right? And so sometimes you see these written as 1 half QV or 1 half CV squared. Okay. We talk about potential difference. That's why a lot of times we use delta V. Now, it is equal to the work required to charge the capacitor, right? And remember, work is delta U over Q. Okay, so there's all these things that you can do, right, in determining, your potential difference and or your electric potential energy and so forth. Okay, now by an extension, we can associate the stored energy with any electric field. So in a vacuum, the energy density, which is given the symbol lowercase u sub e, or potential energy per unit volume within an electric field of magnitude E, is given by UE equals epsilon naught E squared over 2, or 1 half epsilon naught E squared, right? That's the same way to write that equation. Okay. So now let's look at, kind of put a lot of this together, right, into one single problem. And so this problem says a parallel plate air filled capacitor having an area of 40 square centimeters and a plate spacing of 1 millimeter is charged to a potential difference of 600 volts. And we're going to find a bunch of things about it, right? We're going to find the capacitance, we're going to find the magnitude of charge on the plates, we're going to find the stored energy, the electric field between the plates, and then the energy density. Okay. And so we're going to start with what is the capacitance, right? And so we're going to say C equals epsilon naught A over D. And so we're going to do 8.85 times 10 to the negative 12. The area, you do have to be careful with your area calculation here, because it's 40 square centimeters, but that means you have to, because I have a 2 up here, I have to do this twice, right? Or I have to square the factor there. And so I'm going to grab my calculator just to make sure I did that correctly on my notes here. So I'm going to say 40 divided by 100 squared, right? And so I did do it correctly. So it's going to be, my area in meters is going to be 0.004, okay? And it's separated by a distance of a millimeter, so it's 1.0 times 10 to the negative 3. So the capacitance is going to be 3.54 times 10 to the negative 11th farads, okay? And so remember, a farad is our SI unit. Sometimes though you'll see picofarads, sometimes you'll see microfarads, right? And a picofarad is 1 times 10 to the negative 12th farads, and a microfarad is 1 times 10 to the negative sixth farads. Okay. Part B. What is the magnitude of the charge on each plate? Well, all we have to do is Q equals CV, because they're actually going to be charged to the same amount, right? Um, if there's a difference in charge, then you've got, accelerations and forces acting between them. So the plates charge evenly, okay? And so I'm going to do my answer from A, so 3.54 times 10 to the negative 11th farads times 600, because that's my potential difference, right? And so that's going to tell me I have 2.124 times 10 to the negative eighth coulombs worth of charge on in this capacitor. Well, how much electric potential energy is stored? Well, we're going to use 1 half C delta V squared, or you can do the 1 half Q delta V, whichever one you want to use. And so I'm going to do 1 half times my capacitance, so 2.124 times 10 to the negative eighth times 600 squared, because again, that's my potential difference. And so how much energy am I storing? 6.4 times 10 to the negative sixth joules. Okay, so that's the amount of energy that is now stored. Okay, part D says, what is the electric field between the plates? Well, we did this in our previous one of our previous examples where we found it was our surface charge density over epsilon naught, or Q over epsilon naught A. And so I'm going to just simply do Q, which is not 6, but 2.124. So that's going to be 2.124 times 10 to the negative eighth divided by epsilon naught, 8.85 times 10 to the negative 12th times 0.004. So how much electric field exists here? It's going to be 6 times 10 to the fifth newtons per coulomb, right? And so that is my E field. Let me box some of these so we kind of don't get them mixed up. And now the last thing I need to calculate is what is the energy density between the plates. So it's going to be that U equals epsilon naught times the electric field squared over 2. This is part E, right? And so I'm just going to do epsilon naught, 8.85 times 10 to the negative 12th. The E I found to be 6 times 10 to the fifth. And I'm going to divide that by 2. So my energy density between the plates is going to be 1.593 joules per cubic meter. Okay, and so there is our talk about capacitors. Okay, this last problem just kind of took all the little equations that we did talk about and put them into one question. Um, Again, this could be multiple parts on an AP Physics C free response section. But the last thing we're going to do is we're going to talk about dielectrics. Now, the thing about dielectrics, they're very similar to capacitors. We're just no longer, the gap is no longer going to be filled with air. It's going to be filled with some sort of material. Okay.